Hello everybody. This video kicks off a series of videos on this channel. In my previous video I explained the fundamental problem of causal inference, and now we will look at a first set of methods to solve the problem. Namely, we look at methods associated with the propensity score, which is the, spoiler alert, conditional probability of treatment. In this video we look at the intuition for why the propensity score might be important, and we prove that the inverse probability weighting does solve the fundamental problem of causal inference. In the second video, which we'll release a bit later, we'll take a closer look at the theory behind propensity methods. The third video will be a more applied focus. We speak about different kinds of methods that you can use for the propensity score and how you can refine those methods. Finally, in the final video of this series, I have prepared a couple of simulations that illustrate these methods. I thought it would be great to see all the methods we talk about actually in action and how some of the results that we've discussed impact how we should do our estimations. This series is fairly self-contained, and I'll try actually to make the videos fairly self-contained as well. So if you know the potential outcomes framework, you'll be fine. If you have not heard of this framework or you'd like a refresher, check out the link in the description for my video on the potential outcomes. To keep up to date with this series of videos, don't forget to subscribe. As you remember, the fundamental problem of causal inference exists because we don't observe all potential outcomes, but only the potential outcomes of a person for the treatment status of that person. Because people usually act based on their potential outcomes, that means we end up with a selection bias. The selection bias means that if we naively just compare the means of the treated and the untreated people, won't give us any causal effect. All the methods that I present in this series aim at inferring the potential outcomes that are not observed. That means, for the treated, we try to infer the potential outcomes if they had not been treated, and for the non-treated, we try to infer the potential outcomes if they had been treated. Then, using our guess for the missing potential outcomes, we can actually calculate the average treatment effect. Alright, so how do we solve this selection problem? Well, it seems pretty strong to assume that people self-select into treatment regardless of the outcomes that ensue. But maybe if we only compare people who are very similar to each other, then their potential outcomes could also be very similar. For example, if we just compare two random people, one of whom went to college and the other didn't, it seems likely that there's a lot of selection going on. However, if we instead said that both of them are young, white girls with a suburban background and A grades, then it is much more likely that one went to college while the other didn't by pure chance. For example, the internet might have not worked on the day of the applications, so one of them couldn't submit her application and naturally couldn't go to college because of that. Or maybe the one who didn't go to college had a fascinating job talk on opportunities outside of college, so she decided to go for this instead. That's essentially the intuition behind selection on observables. There is selection going on, but this selection happens only based on the observed characteristics. Naturally, there is also a mathematical formulation for the selection on observables. And here we go. We say that the potential outcomes, yi0 and yi1, are independent of treatment, di, conditional on some other variables, xi. That means that once we use our information on the xi, the potential outcomes and the treatment status are completely unrelated. So, what are the consequences of that? Well, there are two primary consequences. I'm giving you them so you have some more intuition on how these methods work. Firstly, that means that if we know the covariates xi, then knowing the treatment status gives us no additional information on the potential outcomes. So we can drop the treatment status from the conditional expectation. Now, why is this useful? It means that once we condition on the covariates, we can ignore whether an individual was treated or not when we infer the potential outcomes. But if it doesn't matter whether somebody has actually been treated or not, since their potential outcomes are still comparable, we have solved the fundamental problem. This here is the intuition behind regression adjustment. If you watch my video on the link between the fundamental problem and omitted variable bias, then you will also see how this assumption solves the omitted variable bias problem. The second consequence is the conditional expectation turned on its head. Once we know the covariates xi, the potential outcomes don't matter anymore for treatment. If you are used to seeing regressions everywhere, this second consequence likely feels a bit more obscure to you. It definitely felt obscure to me. But in some sense, I think this is a bit more natural, because we look directly at the decision problem of the person who selects whether they want the treatment or not. Now, how can we see this? The question is, what does a person know when they decide to enter treatment or not? Well, I would say of these two, this one describes it better, because the person knows their potential outcomes and they also know their covariates xi. But they don't know their treatment status. They're making up their mind about it right now. So in this sense, this is very close to modeling what the person is actually doing. We know their covariates, we don't know their potential outcomes. But, lucky us, the selection on observables assumption assures us that the potential outcomes actually don't matter as long as we observe the covariates. The propensity score is simply the conditional probability that somebody is treated. Because treatment is binary, either you are treated or you are not, this is a Bernoulli random variable, and this probability equals the expectation. Because it is often a bit cumbersome to always write out the full piece, I always write P of xi for the propensity score. So much for some theoretical intuition why the propensity score could be interesting to solve selection bias. As a brief aside, in here you also find a hidden assumption, the so-called stable unit treatment value assumption. This mouthful means that the potential outcomes of an individual do not depend on how many other people also receive the treatment. In a medical trial, this seems pretty straightforward. The new cough medication doesn't depend on whether 20 or 100 or 20,000 different people also receive the medication. In other cases, it might be questionable. The return to being in a social network, for example, increases the more people are in this network. So SUTVA, stable unit treatment value assumption, SUTVA, does not hold. If many more people obtain a college education, then you can actually see that the supply of college graduates increases. So in classic supply and demand equilibrium, the wage of college graduates would decrease. But then a person's potential outcomes are affected by the choices of other people. So the Sutva assumption fails. In practice, you'll have to decide yourself whether Sutva seems reasonable or not. Before diving into inverse probability weighting, which is the main topic, I will briefly look at regression adjustment. This method is probably a lot more familiar to you if you're an econ major. We start with the switching equation, which I have slightly rearranged. You can verify that this actually holds my previous video, but you can also take it for granted here. As a next step, we take the conditional expectations on both sides. So now we've got the conditional expectation, independence on covariance xi and treatment di. Now, if we apply this conditional expectation to the right-hand side as well, we end up with this. Because we condition on treatment, we can pull out the treatment indicator in front of the conditional expectation because it is essentially known to us. Now, if we apply the selection on observables assumption, that means we can actually pretty quickly find out the conditional average treatment effect, conditional on xi. Because if you look at this, this is pretty much a regression where yi naught is the intercept and di is the independent variable, and we've got the average treatment effect here. We can get the unconditional ATE by the law of iterated expectations. Now, there is a slightly hidden assumption here, which is that of common support. This assumption states that the propensity score must be strictly between 0 and 1 for all the covariates xi we have. This is a very hidden assumption. Where do we actually use it? Well, it assures us that these conditional expectations exist. Why do we need it? Well, imagine if we had a certain group of people who absolutely never will be treated. Then to find out what would happen if they had been treated, we can never compare them to people who look similar and are treated, because these untreated people simply look too different. There will never be somebody who looks similar enough and is treated. Now, in regression adjustment, you can get away with some extrapolation. For example, if you use linear regression, you extrapolate the potential outcomes linearly from the people you can actually compare. That might be a decent extrapolation, it might be not. It is certainly an alternative assumption you make in linear regression that replaces common support in those cases. In inverse probability weighting, this does not work anymore, and we'll see that now. Which brings us to the star of this video, inverse probability weighting. Right, let's first look at the tools that we will use. Firstly, the switching equation, as we had before. Secondly, there's a neat trick in the switching equation. Since di is binary, di squared is the same as di, because if di is 1 and somebody is treated, then 1 times 1 is still 1, and if di is 0, somebody is not treated, then 0 times 0 is still 0. Similarly, if you multiply di and 1 minus di, this always gives you 0. Why is this fantastic? Well, it means that we've got di times yi, which arranges to this. It's just the same as di times yi1. It will always give you your treatment status multiplied with a potential outcome corresponding to treatment. Similarly, 1 minus di yi gives you 1 minus di yi naught. And this brings us to inverse probability weighting formula. We can find the average treatment effect with this slightly arcane looking formula. So let's bring some light into this matter. Well, we start with this expectation. Now, the trick we had previously allows us to write this here. We then apply the law of iterated expectations. So now, in this inner expectation, we also condition on the potential outcomes. In this outer expectation, we still only condition on xi. This is the law of iterated expectations. Now, that allows us to pull out the yi1 outside this inner expectation, because we condition on it, so it is essentially known to us in this inner expectation. So we've got yi1 in front, and we've got the expected value of treatment conditional on the potential outcomes and xi. But we know that the potential outcomes are unrelated to treatment once we condition on xi here. But that means that we can simplify the inner expectation. We've dropped the potential outcomes. And you can recognize the inner expectation is just our propensity score. And finally, since the propensity score is a function of xi only, we can actually pull it out of the conditional expectation. After all, if we know xi, we know p of xi, so it is like a constant. And here we are. Now, we found the expectation of yi1, well, conditional on xi. If we just move this p of xi to the other side. But this we can actually estimate. We observe treatment status, we observe the realized outcome, we can estimate the propensity score. Now, if we do the same steps, but instead with the expected value of 1 minus di yi, then we end up with something very similar, but for the potential outcome for the untreated. Now, this looks a bit different from the IPW formula that we've seen earlier. So how do we get to that formula? Well, we can write the conditional ATE as the expected difference in potential outcomes, conditional on xi. And if we just plug in the formula that we've got here after we've moved the p of xi here and the 1 minus p of xi here to the other side, so we can get these expressions. If we've done this, then we can just substitute and get this. Now, the next step is we expand the fractions, which brings us to this term. And it's really simple algebra mainly, some simplifications in the numerator that will get you to this term, which is the formula that we found earlier. Now, the law of iterated expectations then gives us the unconditional expectation. Now, a brief word to explain the difference between the conditional and the unconditional ATE. The treatment effects might differ by the covariates. For example, black people might have a larger treatment effect when going to college than white people due to additional signaling value of a college degree. Now, if we average over all the treatment effects of all ethnicities, we would then find the unconditional average treatment effect. Let's see whether we can find an interpretation for inverse probability weighting. First, we look at how we find the average potential outcome if all people were treated. Now, the problem is, and that's the fundamental problem, that we only observe the potential outcome of those who actually were treated. But the selection on observables assumption tells us that the potential outcomes for people who are similar will also be similar. So, if we want to figure out the potential outcome of people who had a low probability of being treated and therefore were probably not treated, we need to find the realized outcome of the people who were treated but who were unlikely to be treated. That's what we're doing here. The weight increases the less likely it is that a person was treated. The same thing holds to find the average potential outcome if nobody was treated. Here, we need to find people who looked very likely to be treated, but actually were not treated. Thus, when the probability of treatment is high, but the person is untreated, then the person has a higher weight associated with them. Why do we do this? The people who were unlikely to be treated look very similar to other people who are unlikely to be treated. Now, if somebody was unlikely to be treated but still treated, we observe their potential outcome. And since we know that their potential outcome is similar to other people who were not treated, we can use the person who has been treated as a good counterfactual outcome for the other people. To summarize then, we always assign a higher weight to unexpected treatment status. Now, as with regression adjustment, we have the hidden assumption of common support here. It's slightly less hidden than in regression adjustment, but the propensity score must lie between 0 and 1. Here we actually see why this must be true. If the denominator here was 0, then this term would be infinity, and here if the denominator was 1, then this term would be infinity. If somebody is never treated, we can never find somebody who has a similar probability of being treated and who was treated to infer the missing potential outcome, because their probability of being treated was 0. There is something very neat about inverse probability weighting. We didn't need to specify any model for our causal effect. In regression adjustment, we would have to decide whether to include polynomial terms of the covariates, or interactions of the covariates with the treatment, or logarithms. That's not the case for inverse probability weighting. Inverse probability weighting is non-parametric in that sense. The drawback to this is that we do need to model the selection into treatment, and we typically have to make some assumptions there. However, there are lots of situations where IPW is more flexible, so it is a fantastic tool to have in your belt. Alright, this was a lot to take in. The main focus of this video was on selection on observables and the propensity score. The fundamental problem of causal inference is that we never see both potential outcomes of people. A naive comparison typically suffers from selection bias. However, selection on observables tells us that people who look similar also have similar potential outcomes. Inverse probability weighting is one way to exploit this assumption. To find the average potential outcome of treatment and of non-treatment, we increase the weight of those with unexpected treatment status. The next video is on additional theory on the propensity score. It will release in about 2 weeks' time, so make sure to subscribe to my channel. If you enjoyed this video, I would also appreciate a like. If you have any preferences on the series or videos I should do after the propensity score methods, please let me know. Thank you.